So finally in this session I want to look at the initial stage of solid state sintering. So the initial stage is the formation of a net between two particles, shown schematically here, between two identically sized particles, and of course in general that won't actually be true. The radius of the neck is given by x and the radius of the particle is given by a, and it is found for a number of different mechanisms that you can model this by x over a to some power of n equals b, which is a constant, times time divided by a to the n. M and n are both constants, and some values are given here for different mechanisms. And T is the isothermal sintering time. So in other words, it's assumed that everything is happening at a constant temperature, and of course in real systems that's unlikely to be absolutely true. I show here possible mechanisms. So lattice diffusion, clearly going through the lattice. This is lattice diffusion inside the particle. Here is lattice diffusion towards the developing boundary. Surface diffusion along the surfaces, and evaporation followed by condensation here. And note, of course, you've got various curvatures which will relate to the vapor pressures and also the number of vacancies, as already discussed. If we start by considering surface transport mechanisms, these give rise to net growth without densification. Mass flow starts and finishes on a particle surface. If it's surface diffusion, this is the sort of thing that dominates in covalently bonded ceramics such as silicon carbide. An evaporation and condensation mechanism is the sort of thing that you would see in sodium chloride, which is a material that's been studied from a scientific perspective in terms of its sintering behaviour. But as an example of surface transport, because there is no densification, we started off with a set of spherical particles radius r as shown here, we'd end up with a set of cylindrical grains radius a, the height of which is still the same as the diameter of the original particles. And the surface energy of the spherical particle will actually be greater than the surface energy of this cylindrical column, because if we assume, for example, that the grain boundary energy is 1/3 the surface energy, it doesn't have to be 1/3, but it will be less than the surface energy, then for just balancing the total volumes, we've got 4/3 pi r cubed for each spherical particle, and that's going to have to equal 2 pi a squared times r. Remember, the height effectively has not changed. The factor of 2 here comes from the fact, of course, the height of each particle is 2r. Pi a squared is the cross-sectional area. Rearranging that gives us r equals 1.22a. For each spherical particle, the total surface energy would be 4 pi r squared times gamma, which, if we substitute in r equals 1.22a, gives us approximately 6 pi a squared times gamma. For each cylindrical particle, we'll have 4 pi a times r times gamma, plus the grain boundary energy term, which we said is equal to 1/3 of the surface energy term, so we end up with pi a squared gamma divided by 3, and overall, writing that in terms of a rather than capital R, we end up with 5.21 pi a squared over gamma. So a set of circular particles like this would sinter to become a long cylinder of particles, and that has actually been demonstrated with things such as sodium chloride. Of course, if you just started off with a single particle, its lowest surface energy state would be for it to become a sphere. If we look at bulk transport mechanisms, these can result in shrinkage. The mass flow starts in the bulk and finishes on the surface. We have volume diffusion, grain boundary diffusion, which is dominant in many cases. Also plastic flow, and if we were dealing with glasses, viscous flow. So what I've done in this session is briefly introduce the different types of sintering, said a little bit about the stages of solid state sintering, the effect of curvature on vapor pressure and vacancies, and finally says something about the initial stage or necking of solid state sintering.